Okay, so as Daniel said, I'm going to be doing the lectures for today and tomorrow because he's away. And so in the last two lectures, we've been learning about qubits and quantum circuits. And these are the building blocks of a quantum computer. And in the next two lectures, we're going to look at how we could physically implement one of these quantum computers. And so this is predominantly a theory course, so I'm not going to go into very much experimental detail. But it's important to highlight a few of these interesting architectures that exist out there at the moment. And as we go through the course and you guys learn more about quantum information theory, it's also good to kind of keep in the back of your mind that all of these algorithms and protocols that we discuss, ultimately need to be implemented in some sort of physical system. Okay, so before we actually start to look at how to build a quantum computer, it's worthwhile to consider what we mean by a quantum computer. And so in the year 2000, a guy called David DiVincenzo from IBM, he came up with a set of criteria that's now kind of become the standard set of criteria that everybody uses to define a quantum computer. And so this has become known as the DiVincenzo criteria. So we'll first look at that. Okay, so, I want to say, so this criteria, it's not hard and fast, like in the sense that you have to stick to it strictly. It's kind of, there is some flexibility, but it is a pretty good guide to how we should think about a quantum computer. So the first criteria talks about having qubits. So we want to have a scalable system with well-characterized qubits. Now, so it doesn't actually have to be qubits, it could be qubits or some other dimensional system, but it's always nice to work with qubits. And so the important things to notice here is that we want these qubits to be well-characterized, so we want to know what they are. Like you can imagine some sort of machine, some sort of thing that creates qubits and makes many of them, but they're all slightly different. And if they're not well characterized and we don't know, or if they're not all the same, then it's going to be very challenging to do something with that. And we also want it to be scalable, which means that we want to be able to make lots of these qubits. Just one is not going to be enough. The second criteria is the ability to initialize the state of the qubits to a simple fiducial state. And so one example of that is the state of all zeros. And that's reasonable as well. You would imagine that if you're doing some sort of quantum computation, you want to start off with some sort of, simple state. Okay, so the third one is about decoherence. So we want to have long, relevant, decoherence times. And we want these to be much longer than the gate operation time.
have an like order of magnitude?
Well, I guess, so it would depend on how large your computation is, like how many gates you want to perform in some particular, algorithm. So that would be a good way of looking at it. I think I'm not sure what the state of the art is in terms of that ratio. But I mean, you can tell when it's not good enough, and you can kind of tell when it is good enough. So one example is, so for ion traps, which I will talk about later on today, they have coherence times of on the order of minutes, and the gate times are like tens of microseconds, and that's like considered really good. Yeah. And so what we mean by decoherence times is the time that it would take for a coherent superposition to turn into a classical mixture. And so if these times were comparable, then you'd have lots of errors in your gates. So we want to make sure that they're, that one is much longer than the other. Okay, 4. So the fourth one is a universal set of quantum gates. So Daniel talked about this yesterday. And so for this, you want to have single qubit gates as well as entangling gates. And you need to be able to implement these on your actual physical system. Okay, and 5 is a qubit-specific measurement capability. So at the end of your computation, after you've done all of your gates and everything, you want to be able to read off the result. And you want to be able to do that specifically on each individual qubit. You don't want to be in a situation where you can only measure like some bulk property of this array of qubits. Yes?
No restriction to no requirement for correction?
Yeah, so they don't talk about error correction in the DiVincenzo criteria. I'm not sure if it's somehow implicit in any of these. So I think
implicit in number 3. It's like
so
starts decohere, you have a way to kind of fix it, bring it back to a different state.
Yeah, so this is what I was thinking, but I'm not sure if that's the only source of error. So I mean, assuming that your gates are perfect, and assuming that the decoherence time is way, way, way longer than the gate operation time. And assuming that I guess this assumes that you can do all these things perfectly, and if you can't, then, you can't in practice anyway. Yeah, it's a good question. I'm not sure off the top of my head where error correction fits in. Yes? Which error?
Errors could come from many different stages.
Yes. Yeah, so errors could come in the preparation of the qubit. They could come in the implementation of your gates. They could come in terms of the measurement. And then also just interaction with the system, with the environment. So errors could come in everywhere. And I guess, we'll be later on in the course, we'll be talking about error correction, but I guess the idea is that you want to make sure that you can correct or protect against any of those errors. Yes?
I guess, if you have a universal set of quantum gates, then you can do, the protocol system error correction on that. You don't, there's no real more, apart from minimizing the errors, there's no real other way that you've got to
correcting them inherent on the system other than having some kind of set of gates, for instance.
Yeah, so when you say minimize, that could mean kind of two things. One is that you could make sure that your experiment is really, as good as it possibly can be. But then there are other things. I believe they're called decoherence-free subspaces, or there are ways that you can encode your information that protects it from errors. So it's not that you're using some sort of algorithm to fix the errors, but you're using some particular way of encoding them to protect them from errors as well. Yeah. Sorry.
I was basically going to say what Tom said, but I was also wondering how we figure out like what the decoherence time is.
So I talk a little bit about that when I discuss ion traps. But you can, I mean, there are measurements that you can make on your system that, tell you. Yeah, so we'll get back to that. Okay, so these 5 criteria are known as the DiVincenzo criteria. And if you satisfy all 5 of these, then you can, in some good faith, be able to say that the thing that you have can be reasonably called a quantum computer. But you may also be interested, on top of doing quantum computation, you may be interested in doing quantum communication as well. And so in order to be able to do that, there are 2 additional criteria that you need to satisfy. So for communication, so we want the ability to interconvert between stationary and flying qubits. And so a stationary qubit is a qubit that kind of lives in your computer, and since then you do operations on it. So it might make sense to think of to encode a stationary qubit in an atom, for example. While flying qubits are qubits that you want to send from location A to location B, and so it might make sense to encode that information into a photon, for example, because sending an atom from here to the moon might be problematic. And the 7th one. All right, and so you've got these 2 different qubits, and the important thing is that you need to somehow be able to transfer the information from, let's say, your atomic system to your photonic system. And you want to do that faithfully so that then the information can be transmitted. Well, I think, excuse me, ideally, I mean, so you're going to have some sort of information that's initially encoded in the atom. And so that's just its own system. And you want to transfer all of that information to the photon. So after it's transferred, you don't want these 2 things to be entangled. You want them to be separable. But in the process of transferring this information, there's going to be some sort of entanglement between the 2 systems.
But you'd want to, say, be able to take a bell state, and then it's on two different atoms, and then take one of the atoms and encode the part of the bell state that's on this atom onto a photon.
Perhaps, yeah, that could be one thing you might be interested in doing, yeah. Yes, Mike?
I mean, generally, you do some macroscopic measurements and integration.
Let me think. So, yeah, the only way that I can think of converting the information would be involving some sort of, maybe teleporting the state from one qubit to another, which would then require some sort of measurement. But perhaps there is a way of doing it without measurement, but I can't think of it off the top of my head. But is that what you meant? Whether you actually have to make a measurement?
Yeah.
Yeah. Yeah, no, I'm not sure. Okay, and so the last criterion is the ability to faithfully transmit the flying qubits between specified locations. Depends what you mean by scalable. So yeah, people have been able to create systems with, some number of qubits, but I guess creating them with an arbitrary large number of qubits is not possible yet. But
stick in, 500 qubit piece of RAM, right?
So with the ion traps, I think they've been able to trap 14 entangled ions, and so, I mean, okay. So I think there's no fundamental limit to how many ions you can get in a trap. I think there's just a technological limit at the moment.
Okay.
With the other systems. Yeah. I mean, it's kind of wishy-washy. When we go through the ion traps, I'm going to claim that they satisfy all of these criteria. But I guess to what extent? I mean, that's up to you to decide.
How many qubits have people been able to get in ion traps?
14. The last, a couple of years ago, it was 14 entangled ones. I think they can get more if they're not entangled. And I believe that the problem is that not that they can't entangle anymore, it's just that they can't characterize them.
Right.
Because, to do quantum state tomography on 14 two-level systems, it's a huge amount of data that you need to collect to characterize them. Yeah, sorry.
Maybe a year or two ago, there was this company called D-Wave that made
very big claims, and just they seemed like most of the scientific community thought they were tooting their own horn and making claims that weren't accurate, but they got a lot of investment, and I think Google bought them, or IBM or somebody.
Yeah, so
What do we think about them?
I was going to talk about D-Wave tomorrow because I was going to talk about superconducting qubits, and then sort of because they kind of use that in their systems. I don't know if I will talk about it just because I don't know if I've been sick, so I didn't have. I'm not trying to make excuses, but I kind of wanted to be able to say something very good about that, and I'm not sure if I will be able to. It might be worth asking Daniel. He might have something interesting to say about it.
do you know, the scientific consensus that they don't use criteria?
Well, I don't. As I understand it, people don't consider what they make a quantum computer. They don't consider that is a quantum computer. They consider that is something else. So I think, from memory, it's something it's called adiabatic quantum computing, and so I believe that they start with some Hamiltonian and then can slowly tune some parameters and then find the ground state of some other unknown Hamiltonian. So that's kind of the extent to which I understand it, but I don't think they can do arbitrary quantum computations with their systems. And as I understand it, a lot of the criticisms in the past revolved around them just not releasing very much information about what they're doing, and I think they've started to do that more recently, and people have been able to make better assessments of what it is that's going on. But I don't really have a very, very good grasp on that. Yeah. Excuse me? Over just normal simulated and
classical computers.
Yeah.
So that was one of the big criticisms of this isn't a quantum computer because we can't get any benefits that we expect from a quantum computer.
Yeah. I don't know if you've read Scott Aronson's blog, but he's been covering that a lot. He was a really big skeptic from the beginning, and then I believe he's kind of sort of started to give them a little bit. Well, so he thinks they might be doing something reasonable. I don't want to paraphrase him, but I would recommend just looking at his posts on D-Wave because Scott Aronson, I believe the blog is called Shtetl Optimized.
Oh, I think I've seen
Yeah. He was in, recently there was some scandal about something he posted on there. Yeah, so in general, that's a really good blog, by the way, if you're interested in quantum information. Okay, great. So these are the criteria that we would like to more or less try to satisfy. And so now I want to focus on a particular example of an implementation called ion trap quantum computing. And I believe it's the front runner at the moment in terms of which architecture people think will be successful, what is the most likely to succeed in implementing quantum computation. Okay, so in ion trap quantum computing, we use the energy levels of an ion as our qubit. So the electron is going to be either in the, in one of the two lower energy states. And so the way we do it is we start with a group 2 atom. So a group 2 atom is, if you recall the periodic table, it's the second column in the periodic table, and it's all the atoms that have 2 electrons in the outer shell. And so, for example, calcium, excuse me. And then we singly ionize the atom. It's a good question, and I don't know the answer to that. Yeah, can you remind me at the end to make a note of that? Because I think I'd like to answer that, but I don't know off the top of my head. I think I've seen people mainly use calcium, but yeah, I'm not 100% sure. Okay, so then we singly ionize it, so it means we get rid of one of these electrons, and then we're left with just one electron. And so then the 2 lowest energy levels form the qubit. So we have, let's say this is our electron. So we can have the ground state or the excited state, and then we're just going to encode that as our 0 and that as our 1. And so I'm going to claim that this satisfies criterion 1 because we can make a qubit. Is it criterion or criterium? Yeah.
Do you know what the electron configurations are of those, the 2 ground?
In terms of their spin?
In terms of so, if you take, say, calcium, then you've got the 2, it's 1s, 2s, 2 p orbitals are all filled, and then you've got so if you put a single electron into either one of the 2s states, it'd be the same. And so,
single.
yeah.
But you don't, so I don't, let me just try and remember my atomic physics. I don't think you can transition from between 2 different s orbitals, right? So I think it's going to be like an s to a p. But let me double check that and get back to you. Okay, and so we have these qubits, and because they're ionized, we can trap them in a magnetic field. So that's really nice. They can sit in some sort of trap. And then we want to be able to perform unitary operations on these qubits. So we do that with lasers. So we can write down the Hamiltonian, excuse me, of the atom. And so I'm just setting the ground state energy to 0 here. So it's an atom where the energy difference here is E. And then we've got a Hamiltonian that couples the laser to the atom. And so omega is the frequency of the laser, and we're going to set omega to be E on h bar, so that it is on resonance with the atom. And J is a coupling constant that's under our control, so we can, it's essentially related to the strength of the laser that we're shining on the qubit. And this phase phi corresponds to the phase of the laser, so we can control that as well. And so you can see that, just by looking at it, it's going to take the excited state to the ground state, from ground state to the excited state. And here I've assumed that the laser is just treated classically. Like you could do a more rigorous treatment where you consider the laser to be a coherent state, and you've got another Hamiltonian for the electromagnetic field. But, I mean, we don't need to do that. Okay, so this thing is going to be the Hamiltonian of the atom. And that's the atom laser Hamiltonian. You don't, but it's not treated in this Hamiltonian. I mean, if you wanted to model it, you need to do some sort of master equation or something. I don't know if that's the. Actually, no. I think you're right. I think that would be the main source of decoherence. But I guess it's just Okay. So what you do is you pick long-lived energy levels. So later on at the end, we'll see that if we want to make a measurement of the system, then we specifically find another level that's really short-lived. But in order to do, to encode your qubit, I guess they just pick some levels that are really long-lived. Yeah, I'm not exactly sure, because you don't want it to not couple, because you want to be able to transition between the two things. Yeah, right. But you want it to be like,
you want to be able to set J to 0 and then just have it stay.
Yeah, exactly. Yeah. So I mean, that's, I guess, an experimental detail. They try and find some sort of levels that optimize between the two things that you're trying to achieve. Okay, so if we start with a qubit in the ground state, we can, plug this Hamiltonian into the Schrodinger equation and solve it and see how the state evolves. We find that the ground state is going to go to cosine JT. On h bar on the ground state, and excuse me, I've been sloppy and I left out the phases in that, and off the top of my head I'm not sure where they'll go, but let's just assume we've set the phase to 0. But if I had to guess, I think it'd be sitting somewhere here. But I don't quite remember. Okay, so we can see that the ground state probability is going to just oscillate, like sinusoidally. And so if we want to look at the Bloch sphere and see what happens. So we see that we start off in the ground state, and then as you're shining the laser on this thing, it's going to go up here and then come back down, and then we'll do something like that. And so just by picking the strength of the laser and the time correctly, you can do something like a pion 4 rotation or a pion 2 rotation and so on. So you can do any of those rotations. And by changing this phase of the laser phi, what you can do is, in this plane, just change the axis of rotation. So then, rather than rotating like that, you could rotate like this and so on. And so you can arbitrarily choose the axis. Excuse me. So that's almost everything. But the other thing that you want is you want to be able to rotate about the z-axis as well. And so that you kind of get for free, because if you just turn off the laser and see how the state evolves according to just the free Hamiltonian, then you're just going to pick up a phase. So I think G goes to G. And the excited state picks up a phase like that. Sorry. Oh yeah, no, that's.
So this means you can't really, apart from the ground state and excited state, you can't really keep it well.
No, I mean this evolution is kind of happening all the time, and you need to kind of keep track of it. But then you can stop your experiment and let it evolve a while. And I mean, there's ways of keeping track of everything and making sure that it works out. Aww. So I was on Reddit a few weeks ago, and one of these lectures was on there, and in the comments they were totally trashing the lecturer for not knowing how to use the blackboard. So now I'm all paranoid. But they're really challenging to figure out. Don't do it. Oh my god. Okay. What's that?
Oh, if I point out who I am, I'm going to
Yeah.
get as well. So.
In the lectures, you can't really hear the questions anyway.
Not at all.
So then I just repeat what you say, and it sounds like I know what I'm talking about. Okay, yeah, and so I guess, one thing I wanted to mention. So these oscillations, you may have heard the term Rabi oscillations, so that's what that is. Okay, so that's what happens in the ideal case. What happens in practice? Well, we can just look at, let's say we just look at the probability of being in the ground state, and we can plot that as a function of time. So we have probability of being in the ground state goes from 0 to 1. And so we expect kind of this sine squared oscillation, but really what happens is it starts to get damped. And so this is decoherence that's causing that. And so, I mean, I've exaggerated how it's going, but in practice, these, this decoherence time is on the order of minutes. While you can see that, a gate would, kind of be only one oscillation with respect to, how long this thing goes on. Ben? You look like you're about to ask a question. Okay. Okay. So that's great. Like we can do, yes. No, the decoherence time. So, I mean, this thing, I've exaggerated how quickly this decoheres.
So there
In
should be-
reality, there should be like a lot more wiggles for a very, very long time over the course of minutes. But each gate is probably going to be comparable to just one of these oscillations, which will be much shorter. So I'll just write that down. So gate time is on the order of microseconds. But I just wanted to emphasize, you know, what happens to the probability. So you can see that everything's just tending to the identity, because then you've got, it's just a 50-50 probability of finding yourself in the excited state. Okay. So we can do single qubit gates, and we can do them coherently because, you know, there's this big difference between the decoherence time and the gate time. But that's, of course, not very interesting. We want to be able to do entangling gates. And so that's the really cool thing about this implementation. So let's see. And so the way that we do this is we're going to exploit the joint vibrational modes of these ions. So I said before that they're charged, so you can trap them inside a trap using a magnetic field. And so typically people use a linear trap, and so it looks something like this. And you've got your ions, and because they're positively charged, they're all going to repel each other and space out nicely in the trap. And you can imagine that, you know, wiggling one of these guys is then going to have some sort of effect on one of the other guys. So they're going to exhibit this collective motional behavior. And so that's the thing that Sirac and Zola in 1995 proposed to use to be able to implement entangling gates between two of these ions. So so we've got these joint vibrational modes, otherwise known as phonons. And as long as the amplitude of oscillation is small, then we can just approximate this thing as a harmonic oscillator. So the Hamiltonian for the phonons is given by the harmonic oscillator Hamiltonian with a frequency nu. And so now we can have a look at the energy levels of this thing. So we know that we've got the ground and the excited state. So these are the electronic ground and excited states. And we can say that, let's say this is the case for 0 phonons. So then if we want to know what the ground and excited states look for 1 phonon, we're just going to shift everything up by 1 unit of energy corresponding to h bar nu. So for 1 phonon, we have something that looks like that. And because it's a harmonic oscillator, then the next one is going to be just another unit of energy. And so each of these guys is just spaced by energy E. And then each of these guys is energy h bar nu. And then what we want to do is we want to couple a laser. Well, we want to couple 2 of these energy levels with a laser. And so in particular, we're interested in coupling these levels. So to do that, we're going to need to have a laser that has a particular frequency. So let's say this is an energy gap corresponding to frequency omega, which is different to the omega before. And that energy is going to be, well, it'll be E minus h bar nu. And so what happens when we shine a laser of of frequency omega? Well, it's going to couple these guys and couple those guys and couple those guys, and essentially, couple all of the ground and excited states in this. Yeah. So for the single qubit operations, you need. Oh, sorry, no. Yeah, you don't. These don't need to be coupled. I was just. Sorry, I just was denoting the energy levels. So the only thing we're interested in is coupling these two levels and those two levels and so on. So we use laser with frequency omega, and that couples so here we've got a ground state with n phonons, excited state with n phonons, and a ground state with n+1 phonons.
And here, when you say like the frequency, I assume that we have. It's probably easier to tune the strength of the quadratic potential rather than find a new variable frequency.
Yeah, you could have two lasers. There are also lasers that you can tune. I could imagine, in some implementations it being easier to find a tunable laser, and in some implementations it being easier to tune the modes of the trap.
So you do need two different frequencies then, right? One to do the single qubit gates, and then one to...
Yes. And we'll see that we need a few more different frequencies as well in a minute. Okay, so you can see that the ground states of all of these guys are going to be coupled to an excited state, except for this ground state with 0 phonons in it. And so that's important. So because n has to be greater than or equal to 0. Okay, so it'll all become clear in a second how this works. Okay. So we also need one more additional level that is kind of somewhere up here. And we're going to want to couple that level to this state. It's starting to look really complicated, but it's actually not so bad. But for the first step, where we just look at the first atom, we're not really interested in that energy level, but then we need that for the second ion. So, okay, so we initialize everything to 0 phonons. That's important. And now this is how you do the gate. So the first step is to take the first ion, and we take a laser with frequency omega. And we pick our J and our T appropriately so that we do a pion 2 pulse on the state. So a pion 2 pulse should only take you from like the ground to a superposition of the two states. Actually, what am I doing?
So you're going a superposition of the excited state with 0.
Yeah, no, I think a pi on 2 pulse must take you from the ground to the excited state. Yep, sorry. Yes. So I can tell you how it acts on the logical states. So if we have, okay, so the pulse that we're applying is between these guys, right? That's the first one. And so if we start off in the ground state with 0 phonons, then nothing's going to happen because this level is not coupled to anything. So we expect nothing happens. But if our qubit was in the excited state with 0 phonons, then the pion 2 pulse will take you from here to there. So now we go into a ground state with 1 phonon. Okay, so that's the first step. Then the second step is now we're going to be shining some lasers on the second ion. So now we do a pi pulse on the second ion. So a pi pulse will take you from the ground all the way to the excited state and all the way back down to the ground, but you get a minus sign. So you pick up a phase by doing that. So, and now we're going to use a laser that couples this energy level to this other additional energy level. So pi pulse on ion 2. With frequency h bar omega prime. And so we can figure out what we want that, sorry, with energy h bar omega prime. So we want that to be equal to, so this whole energy difference here is E prime. So we expect this thing to be E prime minus E minus h bar nu. So we have E prime minus E minus h bar nu, so then the frequency is this. Okay, so what happens if so, okay, we need to first figure out what all the possibilities are. Okay, so at the beginning, everything was initialized to 0 phonons, right? So our state could have either been, ground or excited or some superposition of those. So we're interested in, E0 and G0. But then because we might have done something to the other ion that, that increased the phonons, then it's possible that the second ion then also could be in this state here. So ground 1 phonon and excited 1 phonon, because the phonon mode is a collective mode of the entire system. So if you, if you're +1 in the first ion, then that's going to give you a +1 in the second ion as well. So these are the 4 things that we're interested in seeing what happens. And because this laser transition is only coupling this higher energy state to that one, that's the only one that's going to be affected. So if you're in any of these 3, nothing's going to happen. But if you're in this state, you're going to pick up a minus sign. So this guy gets a minus sign. And nothing happens to these. Okay, and then the third step is to just undo what you did on the first ion. So we undo step 1. So that means that G0, nothing happens to it. And G1 goes back to being in the excited state with 0 phonons. Okay, so then we can put all of these 3 steps together, and we can see what it actually does on the 2-qubit state. I'm going to get you guys to do that on the tutorial, but it's a C naught where one of the bits is in the X spaces. Yeah. Okay. So in the case where the first qubit is a G, we expect nothing interesting to happen because at the beginning, if you're in the G state, you're not going to pick up any phonons, and so then you'll never be in a position where that second laser does anything to the second ion. So here we just get nothing. And now if the first qubit was in the excited state, it would then be put into the ground state with a single ion. So that's fine. We'll be here, single phonon. So we're somewhere over here. But the second qubit was in the ground state, so it's here. So nothing happens as well. But if the first qubit was in the ground excited state, then the second qubit is somewhere over here. And if it's also in the excited state, then we're in this level. And so then we pick up a minus sign. So this is an entangling gate. And it's typically known as a control phase gate. And so if we can write it C phase. And you can write down the matrix for that. It looks like that with zeros. And so the C phase is C phase along with single unitaries is universal for quantum computing in the same sense that a C naught is. So this is very closely related to a C naught, and in the tutorial tomorrow I'll get you guys to see how they're related to each other. Okay, cool. So have I been keeping track of the criteria? Well, this is criterion 4.
You can do this phonons are collected.
Across the entire linear chain, you can do this with any 2 qubits. But
Absolutely, yeah. Okay. Here we had criterion 3. Okay, and so then the last thing I want to talk about very briefly is measurement. So we're back to having just our single qubit. Hopefully all of the phonon modes are gone now. So we just have ground and excited. And what we do is we find another energy level, let's call it F. And this is a short-lived energy level. So if you put an electron up here, it's very quickly going to decay and emit a photon. And so then what you do is you find another laser that's on resonance with this transition, and you just drive it. So you get a strong laser, and you keep shining it on this transition. And so what happens is if you've got an electron in the ground state, it'll go into the into the F state, and then through stimulated emission, it'll come back down, and you kind of get this like driving transition. But as you're doing that, you'll also like have spontaneous emission of photons, and these are going to go off in all of these directions. But you can put some sort of detector somewhere, and if that detector detects one of these photons, then you know how you've projected the state into the ground state. But if after some period of time you don't detect any photons, then you've projected it into the excited state. And so you want to make sure that you drive this enough so that many, many, many photons do come out, so that if you don't detect any, you're kind of guaranteed that there actually was, you weren't in this ground state. While if you waited for, just a single photon emission, then like that wouldn't be very reliable. So this gives us criterion 5. And then the last one that we're missing is this 2, to be able to initialize the states. But you can just do that through measurement. So you take all of your qubits and you measure them. And so either you'll project them into the ground state or the excited state, but you know what the answer is. And then in the cases where you're in the excited state, you just apply a single qubit unitary and take it back down to the ground state. And so that way you can initialize all of your qubits. And so in order for this to be scalable, you want to be able to combine multiple traps. So either you want to be able to move ions from one trap to another, or you want to somehow be able to set up an EPR pair between them for them to talk to each other. But I think it's unlikely that they're going to make, a single massive linear, trap for a quantum computer. Like you would need to have just lots of smaller traps talking to each other.
Like an optical lattice, spread it out to 2 dimensions.
So, from what I understand, the spacing between the optical lattices is really, really small. So it's quite difficult to address each individual atom in there. But I mean, it's possible. Like people are doing it. But I think that's one of the big technological challenges there.
What's the spacing like between the ions?
It's a good question. I don't know.
The physical, physical distance.
I mean, it's big enough that you can shine a laser. You can focus a laser on one without affecting the others very much.
So it must be good.
Oh no, it'd have to be bigger than that. Maybe.
But they also
I don't know.
they get photons stacked.
If you Google the pictures, you see these kind of, I guess they're fluorescence photos or something, and they kind of the size of the ions, whatever that means, are kind of that big with respect to the spacing between them. But I'm sure if you actually Google the picture, it'll have some sort of, it'll tell you what the spacing is. Because I'm not really sure how to interpret the size of that.
Actual size. So I mean, because you'd have to there'd be some kind of limit between.
I mean, maybe it's an angstrom or something. I don't know.
Well, yeah. But I mean, there'd be a lower limit to how close it could be just by the laser light, right? It has to be big, larger than that.
Right. Yeah, so if you keep putting more and more atoms into the trap, then they, get closer and closer together, and then that's problematic because you then can't address them individually. And also, I think it might be more difficult to keep them cold and having no phonons. Yeah. Excuse me, my God. I hope this cough is better tomorrow. Are there any other questions? Yeah. So tomorrow I'm going to talk about a very different implementation using linear optics. yeah, it's fundamentally different. And if we're lucky, I'll talk about superconducting qubits as well, which are kind of the second runner up at the moment, I think, in terms of a plausible implementation for quantum computing. And maybe they're going to overtake ion traps, from what I've heard.
Done over at IQC, right? They do like linear optics. At IQC, they do linear optics and NMR.
Yeah, David Corey does NMR and he does NV diamonds and stuff as well. But they do linear optics, like Kevin Resch and I guess Ray. I'm not. Yeah.
So would the linear optics stuff be ideal for the communication aspect?
Pardon me?
Would the linear optics stuff be ideal for the communication aspect?
Yeah. So the optics. People usually think about in terms of communication, but in this case, I'm going to be talking about optics for computation. And so one of the advantages is that you kind of get 6 for free, because converting between the stationary qubits and the flying qubits is the same. Although they're not stationary qubits, like you'll see that in the optical implementation, like you actually have these optical circuits, and these things are still flying even though they're performing a computation. But anyway, we'll discuss all that tomorrow. So thanks.